Okay, are there any questions?
Number 7Z.
7?
Yeah. Iron oxide.
Okay. Iron 3 oxide plus carbon monoxide.
But I have another question based on that.
So, iron 3 oxide plus carbon monoxide. 3 carbon monoxides. Yields iron solid plus CO2. For each of the following reactions, indicate whether delta S for the reaction should be positive or negative. If it is not possible to determine the sign of delta S from the information given, indicate why. Alright, so let's take a look at this one here. So we want to predict what delta S is. This is qualitative, and so we're going to just take a guess at it. What do you think? Delta S goes up, down, or stays about the same? It stays about the same. Why? Same amount of gas. You know, the gas is going to have the biggest impact on the entropy. Although CO2 has a slightly higher entropy than CO, why would CO2 have a slightly higher entropy than CO?
Because it's more complex.
It's
That's how it
3-atom molecule versus a 2-atom molecule. A little bit more to it. Yeah, larger molecules are going to have higher entropy, but primarily the entropy is going to be due to the gas. So they're both gases, they're both pretty high entropy. This one, Fe2O3 versus Fe. Fe is very simple, solid. Fe2O3 is a little bit more complicated, the crystal structure goes. But, you know, we have 1 mole of this versus 2 moles of that, so it's kind of break even. And so delta S should be about 0. Roughly.
Like if you have 3 iron and the other one gets 2 iron, can you compare it?
Yeah, no, it's hard to compare because where did the other iron go? You know, if you have 3 irons, it goes to 2 irons, then 1 iron must have went somewhere else. So it depends on where the other iron went.
Like for example, if you have solid, can you compare solid with solid?
Yeah, you can compare solids with solids.
How do you compare? Like, can you give an example?
Can I give you an example?
For example, like you have solid and then you become gas.
Calcium carbonate versus calcium sulfide. Both of these are solid. Which one should have a higher entropy? Calcium carbonate. You know, it's got more atoms. The carbonate ions is trigonal planar thing. You know, it's vibrating. It's just more complex. When we're talking about entropy, this is what type of entropy? You know, the S, the absolute entropy. What type of entropy is that? It's positional entropy. And so when we're thinking about positional entropy, we're thinking about, you know, how many different positions in 3-dimensional space can the atoms occupy? A lot, you know, if it's vibrating and moving around.
Are you recording it? Are you recording this?
I'm sorry?
Are you recording it?
Oh, yes.
Yes,
I'm recording it. Okay.
Can you repeat entropy again?
Positional entropy? Positional entropy is just, you know, how many different positions atoms can occupy in 3-dimensional space. You know, so if an atom is vibrating like this, then it can occupy this whole continuum of positions here that's vibrating.
So it would be higher entropy. Right?
Higher entropy means more ways of ranging things. Yeah. The more ways you can arrange things, the higher the entropy. The more things are constrained, the lower the entropy. Constrained would be if you fix that atom in one position, it can't move. Well, then there's going to be much lower entropy.
So how many types of entropy are there then? You said positional
Positional and energy entropy is
What
the
is
other one.
peak entropy?
Huh?
Peak entropy. Peak, P-E-A-K. What is that?
P-E-A-K, peak entropy? Peak entropy depends on what context did you see peak entropy.
Study on the sample test and you say
What did I say?
The main types of entropy are circle off.
All right. Well, peak entropy. I don't know. Just made that up. Just made it up.
so it doesn't
It sounded like something that would make sense. So that's why I put it on. So there's no peak entropy. What else were the other choices?
Positional.
Positional entropy and
Energy.
yeah, work is not
So we
entropy.
positional
not
energy.
great. Entropy just depends on heat, right?
Entropy can depend on the heat, right?
It's not working related to entropy.
I mean, the heat can be converted into work.
Oh yeah.
Yeah, the heat is discharged.
So work for one of them.
No.
It would be energy and positional.
Yeah, energy and positional, just two forms of entropy. Look at what's the second law of thermodynamics?
The
That's
crystal.
The entropy of the universe is increasing, right, for spontaneous processes. And when we look at the entropy, we're looking in terms of positional entropy and heat. And heat would be the energy entropy, or related to the energy entropy. If you're taking things like you're taking things like this, methane plus 2O2 yields CO2 plus 2H2O. Now here energy is going down. We're going to have delta H that's less than 0. And so we're converting all this chemical potential energy into, this is chemical potential energy. We're going to convert that into heat. And if you think about what you can do with the energy, you know, for methane combustion, you could heat water, right? No problem. Just convert it all into heat, but you don't have to convert it all into heat because they have, you know, compressed natural gas vehicles. So you could use this in a car. You could generate electricity with this, right? And so we can convert this chemical potential energy into work. And you can convert it quite a bit more efficiently converting that than converting heat into work. If you try to convert just heat into work, you know, can you run your car just using heat? You know, let's say you have 1,000 joules of chemical potential energy versus 1,000 kilojoules of heat. Now, if you have 1,000 kilojoules of this versus 1,000 kilojoules of that, this is 1,000 kilojoules of energy. So can't you just do anything with that 1,000 kilojoules of energy? No, unfortunately, because the second law applies to, you know, energy as well, right? Well, actually, to entropy as a whole. You know, so you could have. Anyway. anyway, so it's kind of conceptually it's kind of weird because 1,000 kilojoules of energy seems like 1,000 kilojoules of energy, and you should be able to do whatever you want with it. But it's very difficult to convert heat into work. It's much easier to convert chemical potential energy into work. And so they have something called a methane fuel cell. In the methane fuel cell, what they do is they use this reaction to generate electricity, and there's very little heat produced in it. It's mostly converted into electrical work. We'll look at fuel cells today. Okay, other questions? You don't have to know the details. It's just, chemical potential energy is a higher or lower entropy form of energy. Chemical potential energy, higher or lower entropy than heat. Yeah. Lower. What happens is, as the entropy of anything increases, eventually when everything's dispersed, totally randomized, then the entropy's reached a maximum. Once the entropy's reached a maximum, then there's no driving force for change. I mean, you cannot get more disordered, right? And so, like this heat is, the entropy is quite high, and there's less driving force for change. Okay, other questions? Chapter 19 stuff. How about the battery stuff?
Oh, 19?
Yeah.
What is the range for the temperature? Like we can see it, like
What is the range for what?
what temperature?
Temperature?
Like what is possible temperature that we have?
Like, for example, if you were to heat something up, right?
Like for example, because on the sample test, I find the temperature is 3,348 something Kelvin, and then you ask, is it possible? So I don't know what range should I decide, is it possible or not, like 1,000?
Well, it's okay. Let's say you got the temperature of 3,300 Kelvin.
I think it's not possible.
There's one thing about doing a calculation. There's another thing about actually trying to achieve that temperature in lab. And so there's sometimes a disconnect there, because if people do this calculation, they say, oh yeah, just raise the temperature to this temperature. And so, 3,300 Kelvin, that's borderline. If you said that's okay, that's feasible, then I would have probably accepted that. But that temperature is starting to creep up a little too high. High as in you should know some temperatures. For example, the temperature of a methane. What's the temperature of a flame? This flame. The flame you use in the lab. Methane air flame. 700, probably higher, getting up higher. It depends. Right at the tip of the cone, it should be pretty high. But probably not 1,000 degrees C. And so there are hotter flames like acetylene, O2, and other flames. But all those flames, they can only achieve a certain temperature. You can get much higher temperatures like the sun. And so those temperatures are feasible, but how would you generate temperatures approaching the temperatures in the sun? Because that would incinerate any kind of container that you would have. And so there you have to trap it magnetically or electrically.
and what you generate is plasma. And plasmas are these high energy, high temperature gases. And so it's possible, but you generate plasma, you're going to be incinerating a lot of stuff potentially. It depends on the temperature. There are two types of plasmas that people use. One type, is this low temperature plasma. Low temperature plasmas are like in the fluorescent light bulbs. There's a gas that's electric discharge passes through, generates a plasma. And then you have these thermal plasmas like the sun or plasma torches, those kind of things. Those get very high temperature. And so I usually put that there because some people will calculate a temperature of, let's say, 150,000 Kelvin. If they're getting 150,000 Kelvin, is that temperature something we're going to be able to do in the laboratory? No. And so what I was trying to do with those kind of questions is to put things into perspective. A lot of, and this goes for the whole semester, because a lot of times, we do these calculations, we assume the calculations are correct, but what can happen is that, the real picture is a little bit more complicated. So you go around and you're doing, okay, I got these chapter 18 calculations pretty well down, and then, you find out there are a lot more species in solution. Tyler, did you have a question? No. Okay.
So for that one, the calculation okay, but
I don't know. If did other people get that 3,300 Kelvin? The temperature is getting high. You could say that's starting to get high because you should have a reference point temperature. What's a reference point temperature? You should have some kind of reference point temperature, like the flame. Oh, that's one. Why don't you look up the temperature of different flames? And you can see. Or two, platinum. It has to do with platinum. I mentioned something about platinum. You recall what I said about platinum? Platinum furnace. Platinum furnace is the hot, that's about as hot as you can get with an electric furnace. And how hot does that go? It goes almost to the melting point. Platinum melts around 1600, so you can heat it just below the melting point, 1600 or so degrees C. It's extremely hot temperature for that. If you have a methane air, let's say you have a furnace, methane air furnace, how hot can that get? Like a ceramic kiln or something like that, or these things. This is a reaction that the Romans or the Greeks, who was it? The Greeks or the Romans developed this one. This is thermodynamics in action here. They take limestone and then they throw it in their furnace. They have these high temperature kilns, right? And they make calcium oxide solid and CO2 gas, right? And so they were talking about this because of the architecture. There's a lot of plaster. How do they make the plaster? Well, they, smooth walled plaster buildings versus, the stone and mortar type buildings. Also concrete. How do you make concrete? And so this is critical in this reaction is critical in making concrete and plaster. And so, this reaction is not normally spontaneous, but you can make it spontaneous by increasing the temperature. And increasing, because here you see the entropy of the products is going to be a lot higher than the reactants. And if we can favor the products, then we can get this reaction to go. And so this reaction goes at high temperature, like 2,000 something Kelvin, I think. I forgot. But that's to make it completely spontaneous. You don't have to. You could just kind of push it along. And there are other things you can do. It's not 100%.
Endothermic, right?
Hmm?
Endothermic.
I'm sorry?
Endothermic.
Yeah. Endothermic. Non-spontaneous at room temperature. Once you get to very, very high temperatures, you have to watch out. Because at high temperatures, reactions like this are spontaneous. At very high temperatures, what's going to happen to methane if there's no oxygen around? Methane at high temperatures is just going to break up into carbon atoms, hydrogen atoms. And so at very high temperatures, because this is entropy favored, we're going from methane to all these gaseous atoms, right? And so at very high temperatures, molecules can't exist. Right? Are there any molecules in the sun? Just atoms. Right? Atoms, ions, that kind of stuff. And so the higher the temperature goes, and so when you're getting into very high temperatures, you got to watch out because, let's say this will go spontaneous at 10,000 Kelvin. Well, maybe at 10,000 Kelvin, you're going to tear apart the CO2s, something like that. In the platinum furnace, I put some copper oxide in there. I was trying to make something called yttrium barium copper oxide. Have you ever heard of that? Yttrium barium copper oxide is a high temperature superconductor. It's a ceramic that superconducts at high temperature. Means you can cool it with liquid nitrogen. But when I put it into a aluminum oxide boat, I threw it in our platinum furnace. I pulled it out, and there's a puddle of copper metal at the bottom. And it just got too hot. Left with cool little copper and some other stuff. And so, yeah. What was the question again?
What is the range of temperatures?
What is the range of temperatures?
Like the maximum you can do.
All right, so 1600 is how many Kelvin? 1600 degrees C is how much Kelvin? Yeah.
18.
So maybe up to 2000 Kelvin or something, or 2000. If you start getting to 5000 Kelvin, how are you going to heat that? You can generate a plasma or something. You try to get it that way. But if you're getting a temperature like 25,000 Kelvin, how are you going to get that temperature? Even though on paper, yeah, sure, it sounds okay. Other questions? Number 12. Number 12. You could read it out. Number 12. Estimate the normal boiling point of bromine. Determine delta H of vaporization of bromine from the data in Appendix D. Troughton's rules bait. Troughton's rule. This is a rule. It's not any kind of law or anything like that. What's the difference? In the scientific method, what do we have? We have observation, patterns, trends, to laws. Now, what's the difference between a law and a rule? Well,
A rule is like
a rule is a lot less, what would you say, rigorous than a law? Yeah, a lot less strict. That's a good way of putting it. A rule, you're going to have lots of exceptions, like the solubility rules, you know. You wouldn't call it the solubility laws. Too many exceptions, and lots of exceptions that you didn't memorize. Like, for example, group 1, all group 1 in ammonium are soluble. That's not really true. You know, there are lots of lithium salts that are insoluble. There are even sodium salts that are insoluble. One of them we might even have here is a uranium salt of sodium. Depleted uranium. Most of its activities should be gone. Well, anyway, delta S, Troughton's rule just says that it's about, what, 87, 88? 87 joules per Kelvin per mole. This is just saying a typical liquid, when it gets vaporized, will form a typical gas. What is a typical liquid? A typical liquid is one in which, you know, the intermolecular forces are typically dispersion or London forces. An atypical liquid would be like water. You know, water has much stronger forces of attraction holding the liquid together. And so water deviates from Troughton's rule. In fact, water is over 100, you know, joules per, what was it, 118, wasn't it? 118. That means, was Troughton's rule very good in predicting delta H of vaporization, or delta S of vaporization of water? That was awful. And so Troughton's rule is okay if you're dealing with like organics, your typical organic like hexane, heptane, you know, those kind, toluene. Then it works okay. But the other question comes about is, you know, why bother? You already know, you know, delta S of vaporization. If a liquid is 100 to 200, and a gas is 200 to 300, then delta S of vaporization should be about, if a liquid is about 200 and a gas is about 300, then delta S of vaporization is about 100. Well, you could call that your own rule. It's about 100, and you're going to have some deviations, of course, with that, right? So we have Troughton's rule for this, and there's a whole cluster of molecules that have a delta S of vaporization around 87. And so we could use that as just a general estimate. And so, you know, if we want to figure out the temperature of a phase change, you know, the temperature is going to equal delta H divided by delta S. Delta H we get from appendix D. Even though delta S we could also get from appendix D, we're going to use Troughton's rule to do it. And so here, rather than getting the delta S of vaporization from appendix D, you'll just use Troughton's rule, which is going to lead to an error. And so Troughton's rule I've seen pop up on standardized tests. You know how many times I've used Troughton's rule? 0. That's why I skipped it entirely. But since I saw it pop up on a standardized test, I thought I better assign a homework problem so that at least you might have heard it before.
So it won't be on the test?
No, it won't be on the test. Troughton's rule will not be on the test. Charlton's rule is good in illustrating certain things like deviations, larger. And also, what about delta S of fusion? Is there an equivalent for delta S of fusion? Fusion is going from solid to liquid. Is there a Charlton's rule equivalent? And the answer is no, because the order in solids varies widely, and the order in liquids varies widely, and so there's a lot more spread in there. You got high, you got low, everything in between. You could come up with an average, but when you come up with an average, you gotta remember one thing. What do you have to remember? We could average all the delta S's of fusion and come up with a delta S of fusion average, which is fine. It's going to be delta S of fusion average is going to be about 100, right? Roughly 100 joules per mole Kelvin or Kelvin mole. The reason why that average isn't as good as Troughton's is because the spread is a lot wider. And what names do we give the spread? You call it the standard deviation. If you look at the standard deviations, they're much wider. Or, usually we don't talk much about standard deviations because we only use one. We use about 2 standard deviations, or 1.95 standard deviations for a very large data set. What's that called? About 2 standard deviations is called what? You know what a standard deviation is? Yeah. About 2 standard deviations is called the 95% confidence interval or 95% confidence limit. And so normally what people do is when they write down the data, they'll come up with an average. But we need to know what is the 95% confidence limit here. Otherwise, it's too hard to judge because we can come up with another average here. Let's say the delta S of fusion is about 100 joules per mole Kelvin. And I want to call this Robert's rule or something like that, right? And I want everybody to start using Robert's rule. But a lot of people aren't going to use it. A lot of people aren't going to use it because there's something hidden. They should have told you something first. Whenever you come up with an average, you need to know the confidence limit. Otherwise, what good is the average when you don't know what kind of confidence you can have in that average, right? And so in science, we always calculate the 95%. And so it just so happens the 95%, if you restrict the type molecule here to your typical organic, then the 95% is fairly narrow. And so, it's not too wide. Whereas here, the 95% is just too wide. It's too big of a spread to make it very worthwhile.
Charlton's rule would only really be worth using if you don't have access to the actual value of delta S.
Right.
But then you probably wouldn't have access to the actual value of delta H.
Right. So it's worthless. In a way, it's kind of worthless, unless you have an unknown or mix. If you have a mixture, but still, So yeah, this problem number 12 is kind of ridiculous because here you're going to actually look up the appendix D for delta H and you're going to ignore the S values in appendix D. So that's why I just didn't think I wanted to talk about it. Troughton's rule. Skip it. And I wouldn't even assign this homework, but somebody thought it was so important they put it on a standardized test. Maybe Troughton. Maybe his relatives. No, I'm sure it has its use. I just haven't found it. Okay, other questions?
Yeah, can you look at number 96?
Number 96 from chapter 19? The Gibbs energy available from complete combustion of 1 mole of glucose to carbon dioxide and water. Minus 2870 kilojoules per mole. Okay, A, under biological standard conditions. Now we got a whole bunch of different standard conditions you got to keep track of, right? You have your STP, it's standard temperature and pressure for gases. And then you have your standard thermodynamic conditions. Standard thermodynamic conditions is what? Yeah, 1 atmosphere, 1 bar, 1 molar. What about temperature? No standard. And then we have standard biological conditions. Now what the heck is standard biological conditions?
37 degrees Celsius.
Probably they're going to have a temperature. No? What do you think? 37 body temperature? Yeah. So under biological standard conditions, compute the maximum number of moles of ATP that could form from ADP and phosphate if all the energy of combustion of 1 mole of glucose could be utilized. All right. And so you read that question and you go, I need more information. And so you flip back in the book and they talk about the coupled reactions. Remember that?
Yeah.
And so one of the classic coupled reactions is the formation of ATP. Have you heard of ATP before?
Yes.
ATP is what what would you call it?
Energy band.
The fuel for cells,
Organism.
organisms. Okay. And so let's figure out how much energy is required for that. Wow. This is at the end, very end of chapter 19. To sustain life, organisms must synthesize complex molecules from simple ones. If carried out as single-step reactions, these syntheses would generally be accompanied by increases in enthalpy, decreases in entropy, and increases in Gibbs energy. In short, they would not be spontaneous and would not occur. In living organisms, changes in temperature and electrolysis are not viable options for dealing with non-spontaneous processes. Here, coupled reactions are crucial. See focus on 19-1 on the Mastering Chem website for an example. They eliminated it. It used to be, okay. Did they talk about it in another homework problem?
The solution is really long.
Yeah. All right. Well, you know what? Yeah, I thought they still had that problem in there. So number 96, you can skip that. Basically, it's this. Do you think this happens in a single step in the body?
No.
No. This happens in many, many steps. And do you think all this energy is converted into heat? No. A lot of it's used as work, to do work of building ATP. And so one thing we could do is, and if you take biochemistry, you'll learn all these little steps here, and then you'll learn all these other little steps here. But eventually, what we want to do is we want to use some of this energy to convert ADP into ATP, 3 phosphates rather than 2 phosphates, right? Diphosphate versus triphosphate. And so this is going to require some energy. So all they're saying is assume all this energy is used in work and converting this to this, and how much ATP can you synthesize? And so thermo is very important in biochemistry, obviously. Energy. And so I thought this was an interesting calculation, so that's why I included it on here. But that's part A. Part B, the actual number of moles of ATP formed by a cell under aerobic conditions, that is in the presence of oxygen, is about 38. 38 moles of ATP. Calculate the efficiency. Okay, so what they're doing is they say, okay, once you figure this out, all we need to know is this. We need to know delta G for this, right? Delta G is going to be greater than 0 here. And so what we can do is we can figure out how many moles. And that's our theoretical. You know, in theory, if we converted all that energy into ATP, we would get that many moles. But the actual yield was only 38, and so we do something called the percent yield, right? The percent yield, which would be the actual over the theoretical times 100. And that's also called our percent efficiency. And so calculate the efficiency. What do you think? Is it going to be 100%? No, not even close, because there are a lot of steps here. And the reaction is just not used entirely for ATP synthesis. Consider these typical physiological conditions. The pressure of CO2 is 0.05 bar, the pressure of O2 is 0.132 bar. The concentration of glucose is 1.0 milligrams per milliliter. pH is 7.0. ATP concentration is equal to ADP concentration, which is equal to the inorganic phosphate concentration of 0.00010 molar. Calculate the delta G of conversion. This is very long. Under these conditions. So what we're going to do is we're going to go under non-standard conditions and then calculate delta G. You guys know how to calculate delta G under non-standard conditions, right? Yeah, we use the formula. Right? Delta G under non-standard conditions is equal to delta G under standard conditions. Yeah. Part D, calculate the efficiency of energy conversion for the cell under the conditions given in Part C. Compare this efficiency with that of a diesel engine. Diesel engine that attains 78% of the theoretical efficiency operating at a temperature of 1923 Kelvin, T hot, and the T cold of 1873 Kelvin. Well, forget it. That's more theory, physics. So, yeah, 96. Forget that one. 96. The reason why I assigned 96 is because I wanted you to at least hear about biological standard conditions, and so that's the primary reason I assigned that problem. Biological standard conditions makes you go, what are those? You know? And how do they compare to the other standard conditions? Also, you know, there are people who want to really know a lot more, so they'll dig into that deeper. But for most people, that's all I expected. All right, other questions from the homework? No other questions?
How about when you apply entropy between liquid and waste?
Compare entropy between liquid and liquid. The comparing entropies of liquids can be difficult or it can be easy.
How difficult and how easy?
Well, liquids, like for example, if we have H2O liquid versus CH4 liquid. You can compare liquid water versus liquid methane, although the temperatures are very different, so it's hard to make a comparison, but we'll just look at this. Or actually, let's get something with similar temperatures. Mercury liquid. Which one do you think is going to have a more ordered arrangement of particles?
Probably mercury.
Maybe water because of the hydrogen bonding, or maybe mercury because mercuries are just balls, little spheres, right? Easy to pack. Probably pretty well ordered. And so maybe this wasn't the best one to choose. You know, what you're looking for, well, let's go back to something like CH4 liquid. Here, the water is going to have more constraints, because the hydrogen on water has to match up with a oxygen on water. Otherwise, you have a delta plus repulsion. Whereas methane, is there any constraint in the position of the methane? No. The methanes are much less constrained. So there's another way of understanding entropy, and that is the lower the entropy, the more constraints you're putting on the position. And so here, methane should have a higher entropy because it's much freer. This is a spherical tetrahedral molecule, much less constrained.
That would be the same in the gas state, right?
In the gas state, well, in an ideal gas, the particles don't see each other, so we ignore the intermolecular forces. So in an ideal gas, doesn't. But we also look at the vibrations, and, see what types of vibrations are allowed. Those vibrations will alter the positions of those atoms, which will increase the positional entropy. And so this is why something like NO gas versus NO2 gas, the example they give in the book, which one has a higher entropy? NO2 gas, because there are more atoms, more vibrational modes, they call it. Okay, other questions from chapter 19?
Yeah. Number 17 on the practice. At what H2 factor when it can the reaction be made non-spontaneous at 2 negative 8. But hydrogen at 3 molar, aluminum 3 plus at 0.2.
What was it, HCl and aluminum, or what was the reaction?
2 aluminum solid plus
Two.
6 H plus equals 2 aluminum 3 plus 3 H gas.
So you should know, this is a spontaneous reaction.
Delta G is 485.
Delta G,
485 kilojoules.
negative 485 kilojoules.
Positive. Just positive.
Delta G is positive 485 kilojoules?
Is that a mistake?
That's got to be a mistake.
No,
Are you talking about delta G of formation or
No, it's
delta G of the
Delta G
reaction?
standard.
Delta G naught of this reaction? I said it was 400 plus
It's right
485?
next to it, so it's assumed.
Yeah. Okay, I better look at it. Okay. Unfortunately, sorry. This has got to be a mistake.
This minus.
Well, you know what? I think I didn't change something here. Let me just redo this one because I think, and I forgot to update the file there, but I think I just did it on the board, fixed it. And so let's figure out what delta G of this is. So we'll need, 2 times the delta G of formation of Al3 plus 3 times the delta G of formation of H2, which you should know. What is the delta G of formation of H2? 0. Minus 2 times the delta G of formation of aluminum, which you should know. This has got to be 0. Plus 6 times the delta G of formation of H plus. What is the delta G of formation of H plus? You should know that one too, right? These zeros are different. And we end up with 2 times minus 485, which is negative 970.
So that should be.
Yeah, it's not. That should be a negative. It should be negative. It's going to be negative 970 kilojoules. I'm sorry. There's a mistake on that. On the test. Fix that. This reaction should be highly spontaneous. It's easy to dissolve aluminum in acid. So let's say I don't want to dissolve the aluminum in acid. How could I prevent it from happening? Maybe I could try to go non-spontaneous. For example, if I increase the hydrogen pressure, I could shift this way. And so maybe there's a hydrogen pressure where I can increase it so much that it stops the reaction from going forward. And so let's see if we can figure that out, what that pressure would be. So delta G under non-standard conditions is equal to delta G under standard conditions plus RT ln a Q. All right, delta G under standard conditions we have Q. What's Q going to equal? This is the thermodynamic Q.
It's going to be 2 times 3 divided by 2. Use the oh, I don't use the concentration.
Okay, this would be it. And so I gave some concentrations, didn't I? What was the concentration of Al3 plus?
0.1.
Square. Partial pressure of hydrogen I didn't give, it's cubed. And the concentration of H plus?
Huh? 3 molar? 3 to the 6.
So what do we do with that?
So what we want to do is we want to make this non-spontaneous. So we're going to go from a delta G negative to delta G 0 to delta G positive. So we want to look at the transition point where it goes negative to 0 to positive. So we'll set delta G equal to 0, which is equal to delta G naught, which was minus
70.
970 kilojoules. Okay, plus RT ln Q ln Q is equal to 970 kilojoules divided by RT. Actually, Q is going to equal K now. It's going to be the same number over there. And so K is equal to E to the minus 970 kilojoules. In other words, delta G naught over RT. So what does that come out to then?
What is delta G 0 again?
What we want to do is, do you see, what does this negative mean here?
Spontaneous.
It's spontaneous. So we want to change the second term to be positive what? We want it at least equal to 970, but we need it to be greater. Otherwise, it'll never go positive. And so we're seeing what the minimum or maximum, or whatever it is, that has to be to cancel out this. You know, we want to cancel this term out. Yeah, this is our one term.
R is 8.814.
What did you get?
No, the R value is 8.814.
3145.
It's error.
Yeah, I get an error.
Wait, no, zero is too big.
Yeah, there's an error.
That's positive stuff, right? Positive 970.
Yeah. Oh, you're right. It is positive, huh? It's positive. You gotta be kidding me. Calculator can't calculate this?
I got one.
I can't get anything.
That's
It's error.
E like 7. Do you think it's about
It says error.
I know. It's okay, I don't want to do it. Oh, really?
But you can do it 90.
970 divided by E.
You did?
8.3145 times.
At 1.47.
1.47 times 10 to the something? Just 1.47?
I get an error.
Well, basically, this is going to come out to e to the 970,000 divided by 8.3145 divided by a temperature of 298.
Yeah, that's 392. 391.49.
E to the 391.49.
0.49.
And so, if you get an error, what are you going to write as your answer?
Infinite large. Too large.
You know, yeah, okay. The pressure of the hydrogen gas is going to equal the, actually, do this. It would be 3 to the 6th, 0.1 squared, times e to the 391 cube root. This was in bars or atmosphere? Let me see, the iPhone's got to be able to. Much more. I'm just curious what I'm going to get. 300 and, let's just say 390. Actually, I don't know how to use it. Yeah. iPhone gave error.
How put other people do on the test?
Huh?
How put other people do on the test?
You can bring it out, I'm sure.
No, I'm sure, but you shouldn't freak out because, yeah, you're getting an error, so you got to double check your calculation, right? Triple check it.
Yeah, 1.06 and a temperature is at 170.
Oh yeah. It's because you need to convert the R into kilojoules.
Okay. Yeah, we could either convert the R into kilojoules or whatever. You got times 10 to the 170?
Yeah.
Anyway, this is going to be, even if you do this to the 1/3 power, it's going to be about e to the 100th, you know. E to the 100th is going to be huge, enormous pressure. And so what do you think? Is that something we could do? No. In fact, you got to worry because you get these numbers, and oftentimes you get these numbers, you know, hydrogen is going to liquefy well before then if you put high enough pressure. And if you continue to put higher and higher pressure, it's going to solidify. Do you guys remember phase diagrams? Yeah, it's some ridiculous amount of pressure. And so if somebody tried to say, okay, I'm going to prevent this reaction from occurring by increasing the hydrogen, yeah, theoretically it's possible, but in reality it's unfeasible, right? It's just not going to happen. And so I tried to give you guys a challenge last time. You know, I tried to say, okay, we're going to take this challenge. We're going to try to prevent not only are we going to try to prevent this reaction from pushing electrons left to right, but I want to force the electrons to go backwards in the circuit, right to left. Was anybody successful in getting a negative voltage? You're going to have one more chance today. We'll do a calculation to see. Even the zero is hard to achieve. Well, this time we have a little bit more. Maybe we're going to throw out some concentrated ammonia out there.
Yeah, even though we use the 12 molar,
You use a 12 molar straight? And how much did you add?
we add
You added a lot? Okay, then we have one more thing that I asked to put out. Solid zinc nitrate, I think. I'm going to put solid zinc nitrate out. And then see if you couldn't do it. Well, anyway, we'll take a break for 15 or so and then start.